I'm really very happy and very honored to be here. I would like to thank the organizers and in particular Nicola for inviting me. Actually, that I'm a slightly off subject, not a mathematician, I'm a physicist, and I'm working in non-equilibrium statistical mechanics. So the lectures I'm going to give here are really about non-equilibrium statistical mechanics, and especially fluctuations far from equilibrium and large deviation. And maybe the common point, of course, with the common theme here is that I and the people I work with, we use integrability as a tool to get exact results. A bit in the spirit of, classical equilibrium statistical mechanics, while people wanted to solve models to get exponents, to get phase diagrams. So that's, we don't develop methods of integrability, but we borrow them and try to get formulas. So I will be giving 4 lectures. The first one will be a bit fast, a bit kind of fourre-tout, as we say in French, melting pot, because I want to give you kind of some keywords and some global idea about non-equilibrium stat mech and some themes, but I won't be able to get into the details of all of them. So I will choose 3 topics among the ones I'm going to talk today. And the 3 topics will be the subjects of the next 3 lectures. Tomorrow, I'll talk about the Galavoti, or maybe the day after tomorrow, in lecture 2, I'll talk about the Galavoti-Cohen fluctuation theorem, which is a kind of very general, exact result on non-equilibrium statistical mechanics. Lecture 3 will be using quantum integrability to get exact results on exclusion type processes at the microscopic level. And lecture 4 will be using classical integrability, inverse scattering techniques, to solve exactly some PDEs that describe the hydrodynamic limit of these exclusion type models. Classical integrability versus quantum integrability. Let's start. I will start from the very beginning, which is equilibrium statistical mechanics, to show the difference between equilibrium and non-equilibrium. So at equilibrium, it's a 19th century theory, we have thermodynamics. And thermodynamics is really based on balancing equations about energy and entropy. The first principle tells you that the variation of energy of a system can be accounted for by taking into account the work you do onto the system, W, and the heat you pour into it, Q. And this is a balance sheet that tells you that the energy of the universe is constant. But this balance sheet doesn't tell you in which direction process happens. They tell you that you have to conserve energy, but we know that there's a time asymmetry, and this first law doesn't tell you about the time asymmetry. For example, some machines can be built and some are imaginary. So you need something more than conservation of energy to rule out impossible machines. And thanks to the founding fathers of thermodynamics, Clausius, Kelvin, Planck, Thomson, many others, people, and Carnot, of course, people understood that you need something more than energy to really assess what kind of processes are permitted by nature. And this thing, supplementary, this function is known as the entropy, as Clausius called it. And Clausius understood that the entropy in a real process allowed by nature, the entropy of the universe can only increase. So processes that decrease global entropy, the global balance sheet of the entropy, processes who seem to decrease this global entropy are perfectly forbidden by nature. Okay, and then you have all these formulas that you learned and forgot maybe since then, if you didn't use them, about entropy, which can be computed along a reversible path of the line integral of the heat divided by temperature, and so on and so on. So in kind of layman words, this tells you that all energies are not equivalent. There are higher forms of energies, lower form of energies. Heat is a lower form of energy. And when you convert one type of energy into another one, you need a kind of compensation fee, like putting euros into Canadian dollars. And this compensation fee is the entropy. This is not very precise, but of course it can be made precise. So when you have an open system which exchanges energy and even particles with the environment, this system has 2 tendencies, which are in fact counteracting. The system has a tendency to dissipate and to decrease its energy. and it has a tendency to increase its entropy. But of course, these two requirements are sometimes antagonistic. So you have to find a kind of balance. So the nice picture here is just osmotic pressure. If you put in a U too far, no, okay, I will just wave my hands. If you put a kind of U tube, on the left, you have a pure solvent, water. On the right, you have a solution of water with some, I don't know, salt or sugar, or whatever you prefer, or tea or coffee. And if you have a semi-permeable membrane in the middle, just at the bottom of the U, of course, some water will pour into and try to dissolve the solution to make it less concentrated. So in fact, there will be a kind of unbalance. The water, which was at the same level at the beginning, at equilibrium, in fact, it will be unbalanced. So you can say it's bizarre because somehow I have taken a part of the water here and transferred here. So I've lost potential energy. So it's not good for energy. But because you have dissolved the sugar here, you have increased the entropy of this part of the branch. So the loss of energy is overcompensated by the gain in entropy, and equilibrium is like that. Of course, each time you have to do a balance to understand what you have to do. And the right object to use is neither the energy U nor the entropy S, but for these kind of processes which are at a given temperature, you have thermalization with the environment, the right potential to use is a free energy. The free energy which is given by energy U minus temperature times the entropy. This is a classical formula. And with this object, with this, you can really understand phase transitions and many, many things in macroscopic physics. Okay, that's almost all about classical, classical thermodynamics. One more thing I want to recall you, because if I have time, I would like to tell some things about that in the second lecture. Free energy, I gave you a formula about it, but it has a very strong engineering interpretation, which is very important. If you have a piston with a gas, it's a kind of car motor piston going forward and backward, making the wheels turn and so on. And everything is at a given temperature T. So the gas is enclosed in a container, which is not adiabatic, which is thermally not isolated from the environment. And you produce some work by pushing forward the piston. You could want to know how much work you can extract from this gas piston. And the maximal work, the useful work you can extract from this gas piston, W useful, is at most the decrease of free energy of the gas. One way to remember this kind of crazy formulas is to go back to Galileo. If you have something which falls down, I don't know, water from a fall, hydrodynamic electricity, the maximal energy you can get from it is the decrease of potential energy of your water, of your ball. So here you have to replace potential energy by free energy, and somehow you have the same inequality. So that's a classical work inequality. You cannot do better than that. And the second principle, you have to use both principles to prove that inequality. And the second principle prevents you from doing better than that. Okay. So remember, if you can try to take a photographic memory of this inequality, that the work you can extract is at most the decrease in free energy minus delta F, because it will come back in a different form the next lecture, hopefully, with this so-called Dzerzhinsky identity. Okay, now that's the end of thermodynamics. Just to recall that even somebody like Onsager, we all praise for his solution, among other things, of Ising model, even himself found that thermodynamics and balance sheets were a bit tricky. They are mathematically trivial, but the sign, the plus and minuses and the one-halves are really difficult. And thermodynamics is a difficult subject. So let's now go one step further in time and in science. Forget about thermodynamics. Thermodynamics is a kind of average law of large number theory, average behavior. But underlying thermodynamics, you have statistical mechanics, which was developed by Maxwell, Boltzmann, and Gibbs and other people. And what statistical mechanics tells you is that if you want to describe the microstate of a system, you have to put a probability measure on your microstates. So what StatMech tells you is that the statistical mechanics of a system at thermal equilibrium at temperature T is given by a probabilistic law, and it tells you that a configuration C, a microscopic configuration at equilibrium, has a probability PC, which is given by exponential minus the energy divided by kT, and normalized, so that the probability sum up to 1 by a normalization factor known as Z, 1 over Z. So this distribution of probability allows you to reconstruct the thermal state of any system at thermal equilibrium. So really you have to think in a kind of really a probabilistic way. Each microstate of a system has some measure and some probability to appear. And once you have the law, the probabilistic law, you can reconstruct the thermodynamics. So there is a nice relation, which is nothing but a kind of avatar of Boltzmann's law, S is equal to K log omega, which is written on his grave in Vienna. So this is the same law, just a bit, massaged. And it tells you that the partition function Z, which normalizes the Boltzmann-Gibbs canonical law, is essentially gives you the free energy. The free energy is minus kT log Z. So forget about F is equal to U minus Ts. If you hate thermodynamics, you can just say that the free energy of thermodynamics is just given by the normalization factor of the Boltzmann-Gibbs canonical law. Okay, so you can reconstruct thermodynamics from this probabilistic microscopic behavior. But of course, it goes much farther than pure thermodynamics. Thermodynamics only tells you about average behavior, but once you have a probability distribution, of course, you have fluctuations. You can compute variances or third cumulants or 20th cumulants. You have fluctuations. You have probabilistic description. Thermodynamic observables are the mean values with respect to the canonical measure, but statistical mechanics tells you that everything fluctuates. It's not equal to its mean. There are, of course, fluctuations, essentially variances at least, which is the first signature that you're not deterministic. And these fluctuations are typically Gaussian. So equilibrium is a dynamical concept, okay? And you can go beyond the law of large number. You can go toward central limit theorem and have some Gaussian behavior, or even beyond. We are going to do that and get some large deviations and understand things far away from the typical behavior and even from the Gaussian central typical behavior was so much used with, I don't know. Anyway, so the typical fluctuation, it's very nice to see fluctuations when your average is 0, because then what you see is only fluctuations. Okay, so the typical fluctuating object that was discovered by Brown in the first half of the 19th century is the Brownian motion, the so-called Brownian motion. He was observing a speck of dust, or speck of pollen through his microscope. And he was very careful about experiments and so on. And he saw that this speck of dust immersed in a drop of water was undergoing everlasting, never-ending motion, okay, jittering motion. And he really described that jittering motion in a very precise way. But the origin, the mechanical origin of this Brownian motion remained a puzzle throughout the 19th century. It was even a puzzle for somebody like Poincaré, who really thought it was one of the big problems with relativity in mathematical physics by the end of the 19th century. And as you know, it was in fact addressed and solved by Albert Einstein in 1905. What Einstein understood is that this jittering motion of Brownian motion, of the Brownian, is nothing but the fingerprint at other macroscopic or mesoscopic, because when you use a microscope like Brown did, you are at macroscopic scale. You are at, fraction of micron, 100th of micron. This is macroscopic compared to atomic scale, very macroscopic, mesoscopic. So the Brownian motion is the fingerprint at mesoscopic, macroscopic scale of the granularity of matter. If atoms did not exist, if the Avogadro number was infinite, it means that matter could be broken into pieces, cut into pieces ad infinitum, then Brownian motion would vanish. There would be no Brownian fluctuations. So, I mean, the formula of Einstein, which allows you to compute the diffusion constant of the Brownian motion in terms of the temperature of the system, T. R is the perfect gas constant, it's Boltzmann constant, if you wish. It's just a question of units, it's not important. Of course, the Brownian motion depends on what kind of liquid you're immersed, the viscosity, eta. It depends on the size of the Brownian speck you're looking at. Typically, if it's a sphere, A will be the diameter of your pollen sphere. And it's proportional to 1 over the Avogadro number, n, which is 10 to the power 23. So if n were infinite, D would vanish and Brownian motion would disappear. This is an incredible formula because if you look at this formula, everything in this formula but the Avogadro number is macroscopic or mesoscopic. And 1 over the Avogadro number, if you remember the definition, the Avogadro number is how many atoms of hydrogen you have in 1 gram, or how many atoms of carbon you have in 12 grams. So 1 over the Avogadro number is the weight of the proton, of the hydrogen atom, okay? So it means that in fact, this formula of Einstein is among the very first ones. Maxwell had a formula a bit similar about viscosity, but it's the very first one, very clear, that connects mesoscopic with macroscopic with macroscopic. Something at the atomic scale and something at our scale. Yeah. So D, yeah, sorry, I should have. Thank you for the question. So what Einstein understood is that you should not look at this trajectory as a classical trajectory with a nice speed and position and so on. You should look at it as a stochastic object. And of course, because everything is isotropic, on average, the position of the Brownian particle is 0. It's where it started from. It's totally isotropic. So the object that you should use to characterize it is the x square, is a square average, and x square grows linearly with time. So average of x square is d times 2d times t, and d is given by this diffusion constant.
When I look at the dust in the sun, is it a Brownian motion?
The dust in the sun.
You have it on your window.
Yes, I'm not completely sure. There could be a thermal gradient also, because you have this ray of sun coming, and there could be some heat gradients also. So there could be some vibration of the air. I think people like Gui in the 19th century also ruled out the fact that you had a mechanical vibration and thermal gradients and so on and so on. Could be also, so many people in books say that this is a kind of Brownian motion, but I'm not so much convinced. You should ask an experimentalist. I'm no more an experimentalist than you are, as you know. But yeah, we should ask an experimentalist. Okay, so let's continue. I want to finish with equilibrium. Einstein had another brilliant idea. He wanted to understand, so equilibrium is a dynamical concept. At equilibrium, you have fluctuations. So you have something which goes beyond thermodynamics and averages. How can you characterize these fluctuations? So Einstein had the brilliant idea that you should invert Boltzmann formula. Boltzmann formula tells you that the entropy S is K, Boltzmann constant, log of the number omega, log of omega, and omega is the number of microscopic states that underlie a given macroscopic. If you have a macroscopic state, a bottle of water, you can characterize it by a finite number of observables. The size, the volume, the temperature, the pressure, the color, I don't know, the name of the brand, but only 10 or 20 or 100 if you can think about. But your bottle of water contains 10 to the power 23 atoms. So anyway, there's a huge reduction of information when you go from micro to macro. Huge, absolutely huge. 20 orders of magnitude, 20 orders of magnitude. So when you go from micro to macro, a macro state, a given macro state, which seems to us to be still and constant and well-defined, in fact, under this macro state, there's an absolutely huge number of microstates in which atoms are in different positions, but which give you the same impression, which give you the same macro state. So you have to count how many microstates correspond to a given macro state. And you call this number omega, and the log of omega, the length of this number, is the entropy. Yes, in W was the old notation. I think now people use omega, but but on the tomb, it's a W, indeed. Planck wrote this formula. So Einstein had the idea that you should invert that formula, and you could use the formula of Boltzmann, knowing the entropy from thermodynamic calculations. You could use the formula of Boltzmann to compute the number of microstates underlying a given macrostate. Yes?
The entropy formula you mentioned is only for the microcanonical ensemble.
Yes, okay, then you replace it by the free energy. Then it becomes yes, completely, yeah, of course. Yeah, sorry, yeah, indeed. But then it becomes how do you say that? It becomes just technique. But the master formula is Boltzmann formula. I even wrote F is equal to minus KT log Z, which is already an avatar of this formula. And then you have different avatars and different ensembles.
When you think of W, you always say, oh, it's the logo.
I prefer to say it's just the length of the number, the information coded in the number. Okay, so what Einstein said is that you can count the number of microstates corresponding to a given macrostate just by knowing the entropy of the macrostate, by inverting Boltzmann formula. And then, of course, the most probable state is the one with the maximal entropy, and it's exponentially, because the entropy S is proportional to the number of particles. It's what we say an extensive quantity. So it's of course proportional to n, the Avogadro number. So it's a huge number. And this omega, of course, the most probable state is the one with the biggest entropy. What I'm just using here is a saddle point method, trivial saddle point method. I just say that the state with the highest entropy is overwhelmingly more probable than the others. But of course, you can always try to find a state which has slightly less entropy, so by making just an expansion around the saddle point, and this will give you naturally Gaussian fluctuations. I want to enter into the details because we shall go to large deviations and enter the details, but you can take this exercise as a kind of, test bed. You can estimate what is the probability that a grain of sand of 1/100th of gram, which is on the ground, will make a spontaneous jump in normal conditions, 40 centimeters up. This is possible, but what is the probability? So I let you think about it. So the entropy has some natural variables. As you know, I mean, we always learn that entropy is a function of energy, V. Yeah, of course, it's second derivative. It's a maximum. Yeah, I forgot to say that the second principle tells you the entropy is maximal. So if you take a derivative, it's negative. And if you take a derivative and take to second order, because it's a maximum, the first order vanishes, it gives you a Gaussian distribution. So this tells you about the probability that a macroscopic system occurs in a state which is not the most probable one. In one state, which is not the most probable one. So it tells you the probability, for example, I don't know, that suddenly the pressure in a room decreases by 0.1% for some reason. We want to understand something more important. We want to understand dynamics. We want, for example, so this is a non-equilibrium process, but it's easier to explain. We want to send a current through a wire, and with a given difference of potential, and the wire has some resistance R, so we know that the current is U over R, Ohm's law. But if we plot the current, or if you measure it very precisely, of course, you will not see a constant current, you will see fluctuations. And we want to characterize these fluctuations. So that's a non-equilibrium process, but I told you, let's take the example that the pressure somewhere in a room is 10% less than, 0.1% less than the typical pressure. But now we want to monitor the pressure somewhere with time. So we want to see the time series and understand time-dependent fluctuations. So to understand that, we really have to go beyond Boltzmann formula, which is static. There's no time here. And we have to go beyond thermodynamics, because in fact, thermodynamics has no dynamics, has no time embedded in it. So we have to go slightly further. And this was done by Onsager in the 30s. Onsager was interested in the so-called linear response theory, is when you have a system at equilibrium and you put some external constraints, some external drive, brings it slightly out of equilibrium and drives currents through it. For example, you take a wire of metal and you put a very small difference of potential on two sides of the wire, then there will be a small current going through the wire. Okay. Or you take a cube of material and you put three differences of temperature along the width, the length, and the height, delta T, which are small. But even if they are small, there will be some heat current passing through your cube. And what on Sager, of course, at first order, we want to do linear analysis. So if Ji is the current, we know that the Ji's will be proportional to the gradients of the temperature. And you can write a matrix phenomenologically, Lik, which relates the gradient of the temperatures along the three directions and the currents which are developed along the three directions. And there's a matrix between them. That's just a tensorial relation. And what Onsager discovered, and this is just one example, but in fact his law is much, much more general. You can apply it to see piezoelectricity, magnetostriction, I mean, many, many things. With some very general hypotheses, the matrix that you get that relates the stresses and the responses, the gradient of the temperature and the fluxes, the currents, this matrix is generally symmetric or antisymmetric if you have some magnetic field or some rotation. But it's typically symmetric. You can say, okay, I mean, it's nice, but why? Why is it important? It's important because it allowed Onsager to really develop a theory of thermoelectric effects, which was a kind of open problem at that time. And it also allowed him to predict many, many effects which were not seen at that time. Because if you put a constraint A and you have a response B, it tells you that if you put A as a constraint, you will have B as a response. If you take a piezoelectric crystal and you stress it, you will get a difference of potential. But if you put a difference of potential on a piezoelectric crystal, then you will have a mechanical stress. So it allowed him, just by the fact that you cannot have Lij equal to 0 or Lij non-zero and Lji equal to 0, it allowed him to predict and also to give a order of magnitude of many, many effects which are not known. So this owed him the Nobel Prize, in fact, not the Ising model. He got the Nobel Prize for that, quite amazingly. Well, he could have got two, in fact, but got only one. Okay, so these are known as the reciprocity relations of Onsager. And then 20 years later, and now we are getting much closer to our subject, Onsager and Mallick used these reciprocity relations to address the problem I just told you about. How can you characterize not only static fluctuations, but fluctuations with time series of some phenomenon, whose probability changes, and you want to see how it, I mean, not only the position of a Brownian particle, but the whole trajectory. It's path probabilities and not only final position. So what Onsager and Mallick discovered is that thermodynamic quantities that I call X here, could be the temperature, could be the volume, the pressure, the concentration, whatever, let's call it X. At this linear response order theory, so we are only in the linear theory now for the moment, they satisfy a Langevin, a stochastic differential equation. So X is a vector of some thermodynamic quantities, and its time derivative is given by some matrix that I call LA times X. Okay, so this would be a purely deterministic problem, but you have to add to it a noise, a Gaussian, a white noise. And this gives you a Langevin stochastic differential equation for which you typically get some Gaussian process because it's linear, and you can do the statistic, the time-dependent statistic of the stochastic evolution of these thermodynamic variables. So you see, just to recapitulate, thermodynamics gives you only averages. Einstein theory of fluctuations tells you that these averages, or statistical mechanics, which he was one of the main developers, tells you that in fact these are averages with respect to some probability law, and in fact there's a distribution. And Onsager-Mallick theory tells you how this distribution evolves with time. So it tells you that it's not only a given time distribution, but it's a whole trajectory that you can characterize. And once you have a stochastic differential equation like that, you can write a path integral. You can write what is the probability of observing a given path, a given evolution between time 0 and t. And this is the so-called So in physics, we call it the path integral. The more mathematically inclined people will call it the Wiener measure. All these are Gaussian processes, and the Onsager-Markov theory tells you what coefficients to put into this Wiener measure, and you retrieve in these coefficients the matrix L, which is nothing but this Onsager linear response matrix, and the matrix A, which is nothing but the Hessian, the second derivative, negative definite on the second derivative of the entropy that appeared in Einstein's theory of fluctuations. So you have to combine all that and write the stochastic differential equation to get a probability measure on time evolutions, time series of thermodynamic quantities. But all this is at equilibrium. I wanted to tell you and to go into the details for that, because when I don't pretend that, okay, I explain that in details and so on, but once you have these kind of ideas in mind, and all this is near equilibrium, you understand much better how the more recent theories, for example, this macroscopic fluctuation theory I'm going to tell you about later on, which was developed by the Rome group around Gianni Giornalasigno, you understand how these theories, in fact, generalize these kind of ideas in the nonlinear and far from equilibrium context.
This is an equation for thermodynamic variables. Is there something for the Boltzmann distribution and how it varies?
So once you have this equation for thermodynamics variable, you could write a kind of formal Fokker-Planck equation for the Boltzmann, for the evolution of the distribution. So this would be the equivalent of Fokker-Planck, but at the path level. But of course, all this is close to equilibrium. So what this MFT, macroscopic fluctuation theory, tells you, it gives you, I'm not going to write it like that, but I'll just give you the answer. They could write Hamilton-Jacobi-Bellman equation for the evolution of distribution for a large class of systems out of equilibrium, but with some, of course, you need some hypotheses. So you need some local equilibrium, you need some scaling, some diffusive scaling, but it's much more general than that, and it goes into the nonlinear regime. So that's the idea, indeed. Okay, so I think now, just to finish this first part, how much time do I have left? 25 minutes, okay, half. This first part about non-equilibrium thermodynamics, which is in fact just linear response in the vicinity of thermodynamics. Thermodynamics is about average values. At equilibrium, a system in thermodynamic state does not exchange matter, information, energy, spin, charge, whatever you like with its environment. On averages, all these exchanges, all these currents or fluxes are zero. Of course, they have some fluctuations, but they are zero on average. Thermodynamic equilibrium obeys time reversal invariance. And I remember now, I see that I forgot to tell you that, and this is very, very important. The physical principle behind the fact that this matrix is symmetric is something very deep, is the fact that physics at the microscopic level is invariant by time reversal. Although macroscopic phenomena do not look so, if I throw a glass of water and break it, it will not come back to my table, this is well known. But microscopically, apart from some weak interaction thing, but microscopically, most of the laws of physics, apart from weak interaction, are time reversal invariant. And for example, this law of Onsager is the signature at the macroscopic scale of this fundamental symmetry of microscopic physics. Physics is time reversal invariant. Therefore, this matrix of Onsager is symmetric, highly non-trivial. It's a deep result. We are going to prove it in the second lecture, by the way. So the crucial property behind this Einstein and Onsager relations are time reversal invariance of thermodynamic equilibrium. If you take a movie of a system at thermodynamic equilibrium and show the movie backwards, nobody will be able to say that it's going backwards. But equilibrium is a dynamical state. You should not think about equilibrium apart from 0 Kelvin temperature, which is not reachable. But at any finite temperature, equilibrium is a dynamical state, always moving, always evolving. and it's not as dull as it seems. So Brownian motion is not a dull object at all. There's a nice, I will probably leave the slides here. There's a nice quotation from a book written by an Indian author called Tarun Tejpal, which I think characterizes well what equilibrium is. The fact that you think that the world is a stable quantity, but in fact there are always fluxes and things are fluctuating. So summary, if I take again my wire with the two reservoirs at temperatures T1 and T2, if T1 is equal to T2, I can apply statistical mechanics at equilibrium and thermodynamics. If T1 and T2 differ very slightly, delta T over T is very small, I can apply linear response theory on Sager, Einstein, Kubo, and so on, which was developed from the 30s to the 60s, all this theory of linear response. And you can even define some entropies, near equilibrium, entropy production. But all these ideas will be inefficient, not to say worse and useless, if you go far from equilibrium and the two reservoirs on the boundaries have very different temperatures or very different potentials. Then you have to do something different. So, and indeed in nature, many systems are far from equilibrium. So now we can enter our main topic, which is non-equilibrium statistical mechanics. I don't know why he does that. So again, this is the picture you see in almost every seminar at the beginning of every seminar in non-equilibrium stat mech. This paradigm of a wire of metal which connects two reservoirs at different temperatures or different electrical potentials or different concentrations so that they drive a current through the wire. For this kind of very simple object system, there is no macroscopic theory. There is nothing which would play the role of macroscopic thermodynamics. We don't really know what are the relevant macroscopic parameters. We should certainly put the two temperatures on the boundaries, the length of the system, maybe the current, but we don't know if it's a complete set of observables. We don't, even if we knew these parameters, we don't know in which functions we should put them. In physics, we like to have optimization principles. Entropy is maximum, energy is minimum, free energy is minimum. I don't know, Lagrangian action is maximum. But we don't know which functions should describe the state of the system. We don't know if there is kind of universality. What are universality classes? Nothing which plays the role of a microscopic measure like the Boltzmann-Gibbs Maxwell canonical measure, exponential minus e over kt. We are not going to put exponential minus e over k t1 plus t2 over 2 or square root of t1, t2. All this is wrong, so we don't know. And typically, because there is a current driven in the system, there will be some long-range correlations, and therefore non-Gaussian behavior will appear. Because Gaussian behavior comes finally from the central limit theorem. The central limit theorem comes from the fact you add independent random variables, and independence comes from the fact that you have you can break your system into locally independent systems because the correlation length is finite. And when you have a big system, you are adding many independent systems and you get something which is Gaussian in the end because you have the central limit theorem. If you have a current driven to the system, you have long-range correlations. What happens on the left depends on what happens on the right. So you have a kind of string, it's not string theory, but you have something long-range which is going on through the system. And typically you will have law which emerge, which will be non-Gaussians. You will have long-range correlations. So one of the important observable out of equilibrium is the fact there is a non-vanishing average current. So many people concentrate on calculating distribution of the current, time series of the current, large deviation functions of the current, and we are going to take this point of view. So there are two strategies to try to address these questions. There is up and down and down and up. Up and down would be to do a bit things a la thermodynamics, which is to find very general laws, which would apply if not to any system, but to very large classes of systems. And to try to find some identities, some balance equations, some equations, which connect different things and which can be applied to very many different systems. Since the end of last century, last 2 decades and a half, some important, very important progress was made in that direction. And this will be the subject of lecture 2. And they go into two. One is called the work identities. You may have heard about Dzerzhinsky. He was the first one to identify them. So they are also called Dzerzhinsky identities. And they really extend a thermodynamic theorem, like the one I showed you about 10 minutes ago, which is the maximal work theorem. You cannot extract more work than the decrease of free energy. Dzerzhinsky was able to find something beyond that. And that's quite striking because nobody could believe that 150 years later, there would be something which was not discovered in classical thermodynamics, that one should have to add one more chapter in all thermodynamic books. Something which is more mathematical and which was discovered by many people and which goes usually under the name of the Galavotti-Cohen fluctuation theorem is the mathematical property of large deviation functions. So it relies on large deviation theory. And they show that on Sager identities, which relied on time reversal invariance, they can be generalized. And there's a kind of more general property of large deviation functions of currents or some other quantities, which in fact contain on Sager identity, but which are valid at the functional level. On Sager identity will appear as a kind of second order derivative of their general fluctuation theory. So this is lecture 2. And there's a so this is from up to down, and there's a down to up point of view, which is maybe more dear to many of us, at least to me, which is to try to understand things by solving models exactly. Just like people try to understand phase transition by solving 6-factors models, Ising model, ice type models, and so on. So there are some paradigms, some very nice models, which happen to be solvable, which can be analyzed very thoroughly. And these models give us some understanding about more general behavior. But these models can be studied mathematically in high details. And also these models, once they are solved exactly, we can use them to understand more general theories, more versatile theories, hydrodynamic behavior, and so on and so on. So all these ideas rely on the concept of large deviations. Large deviations are an extension of the two basic theorems of probability theory, which are the laws of large number and the central limit theorem. So the idea is the following. You take a coin, throw it 1,000 times, 1,000,000 times, and head and tails. Suppose it's head and tail, one half, or if it's a bias coin, it's P and Q, and you want to count the number of heads, and you know it will be 500,000 plus or minus square root of 1,000,000, which is 1,000. That's a typical. So the law of large number tells you that if you count the number of heads and divide by number of trials, this would converge to 1/2 in the large n limit, large number of trial limit. The central limit theorem tells you that if you count the number of heads, you subtract its average value, which is 1/2 the number of trials. You divide by square root of n, n being the number of trials, you get a Gaussian normalized law. These are the two basic, somehow non-random theorems of random theory, of probability theory. This is the laws of chance. But you can go further, and you could ask the following question. I call Sn the number of heads, and n the number of trials, 1,000,000. And I want to know what's the probability that Sn over n is 1/3. So something non-typical instead of 1/2. Then you can show that this probability, in fact, adopts the form of large deviation. This probability is of the form exponential minus n, the number of trials, times a rate function phi of r, which we also call the large deviation function. And this rate function phi of r quantifies the rare events. Of course, for r equal to 1/2, this probability is 1 in the large n limit. So phi of r, phi of 1/2, because it's almost 1 probability at the typical case. But if you know this function phi of r, you can compute what is the probability of seeing 3 times more heads than tails. This large deviation theory. Okay, for this real case of a Poisson random variable, just by using binomial, Poisson Bernoulli distribution, you can compute everything. But you can ask this question in a much more general way. For example, you can stand in a room with a gas, closed room, which is not exchanging air with the surroundings at a given temperature T. And you know that at equilibrium, there will be a even pressure and even density of air throughout the room. But then you can ask a kind of strange question. You can take a volume here of 1 liter and measure the density of air in this 1 liter volume. Of course, typically it will be the same as the average density, but you could ask the question, what is the probability that I measure here and I have an empirical density which is 10 times less than the average density or the double of the average density. This is very, very unlikely. And again, this probability distribution of seeing an empirical density, small n is the number of molecules in my small volume V, small v is 1 liter. So the probability of seeing my empirical density equal to rho is also taking a large deviation form, exponential minus this volume times the function phi of rho. And of course, phi of rho vanishes at the typical density rho 0. And now comes the very nice result, and I think it was developed in the 70s by mathematical physicist called Ellis, who wrote a book about that. You can ask this question and try to compute phi of rho. Well, this phi of rho is, apart from some constant and so on, nothing but the free energy of the system. There's a constant beta, which is 1 over kT, and so on. But essentially, trying to find the large deviation function of the empirical density of your system is a way of defining the free energy. So that's the third way of defining free energy that we saw today: thermodynamic, U minus Ts, stat mech minus kT log z, or purely probabilistic. You try to find the large deviation function of some observable, and in the case of a system at equilibrium, this defines you the free energy. So you don't need to know anything about thermodynamics, entropy, and so on. You just have to ask some probabilistic question about some well-chosen observable. And if you're able to solve this probabilistic question, and if you ask this question to a gas at equilibrium or a liquid at equilibrium, you will retrieve the free energy. But the nice thing is that this question, you can generalize it. I told you that I took a small volume of 1 liter, but of course I could ask, what is the probability of seeing a density profile in the room? On average, it's a flat profile given by rho 0, but I can have slightly more here, slightly less there, and have a shape. And I want to know what is the probability measure on this function, this 2-dimensional function, a bit like your question before. Okay, so I want to have a probability measure on surfaces which represent the local density in space. And again, it takes a large deviation form with this function f twiddle, go take f, and this function f twiddle becomes a function of the density profile. It is the one which will satisfy this Hamilton-Jacobi-Beltman formula in the general case. And okay, so that's very nice. But now, if you compute it for a gas at equilibrium, you will see that this functional is nothing but the integral of the free energy. Minus, it's just a normalization thing. So again, the free energy is the kernel of your functional, of your large deviation functional. Okay, so you can retrieve the free energy knowing this function. The message is that free energy of thermodynamics can be viewed as a large deviation function. And now comes something very nice. I told you that before we cannot define the entropy far from equilibrium using the old formulas U minus Ts, or we don't have a microscopic probability distribution. We cannot define the free energy out of equilibrium, but this kind of probabilistic questions, we can ask them out of equilibrium. Indeed, if we take, again, let's take the picture here. If we take again our system with 2 reservoirs at different temperatures or different potentials, high potentials on the left, low potential on the right, we know that on average, the profile of temperature will decrease linearly. We know that. That's just Fourier's law. But of course, there could be fluctuations, and for some bizarre reason, it could adopt the non-linear red curve, which is there. And we can ask the question, what is the probability of seeing this distribution of temperature of a bar of metal connected to two different reservoirs at two different temperatures. If we were able to compute the distribution of any curve joining T1 to T2, we would get something which at equilibrium would be the free energy. So out of equilibrium, it would be a good candidate to be something which plays the role of the free energy. So the question is, what does its functional look like for a non-equilibrium system? So unfortunately, there is no general solution to this problem, but using integrability, one can compute that for some toy models. More generally, we can look at the current. So as I told you, we have a typical current in this model given by Ohm's law. The difference of potentials of temperatures on the two boundaries divided by the length multiplied by some distance gives you the typical current. Is the transport of heat or transport of molecules from left to right. So there's a certain given number of particles which went from left to right, or current which went from left to right. And as you remember, the current is nothing but the total number of particles or charge which flew from left to right between time 0 and t divided by total time. So this is the empirical rate of transport of current or charge. A current is the empirical rate of transport of charge, Q over T. But by chance or bad luck, you could make your circuit and empirically during a given time get twice more or 10 times less current because of some statistical fluctuation than what you would have expected. This would be very bad for your electrical installation. So you have to find a way of assessing the risks of that thing. Large division theory comes also from risk theory and this kind of, yeah. What is the probability that the empirical current small j, qt over t, during a time t, small t, takes some value, yeah, j. Again, a large deviation behavior, phi of j, and this function phi of j vanishes at the typical current, capital J. And also, this function phi of j, you can show that it is convex. So it vanishes at the typical current, it's convex, it's minimal at the typical current, 0, it's always positive because the probability is less than 1. So of course, phi of j has to be positive. So it's a kind of bell-shaped curve. It's a kind of potential. Physics likes bell-shaped curves. When you go to the bottom, you are the typical state. So all this is a hint that indeed these large deviation functions are good potentials which can be defined even out of equilibrium. Okay, I still have a few more minutes. 5, yeah. So it's good. I can maybe, yeah. Of course, I said less than what I wanted, but I can arrive to the Galotti-Cohen fluctuation theorem. The Galotti-Cohen fluctuation theorem tells you that under very general hypotheses, these large deviation functions, for example, the one for the current here, phi of j, is essentially an even function. Phi of j is a very complicated function, but if you subtract phi of j from phi of minus j, you get something which is exactly linear, which means that in fact, the function phi of j minus alpha over 2j or plus alpha over 2j is an even function. But alpha is some coefficient which depends on your system. So it's a kind of very strange symmetry of this object that we don't know how to compute it a priori. It's a complicated object, but it satisfies some symmetry. And what Galotti and Cohen showed, and many people also like Leibowitz and Spohn and other people, Kurshan, showed that this property, this very generic property of large deviation functions comes from the fact that microscopically, whatever you study, even this kind of object which seems to be very irreversible, microscopically, the physics that drives it, the laws, are time reversal invariant. At a macroscopic level, the fingerprint of this time reversal invariance, microscopic time reversal invariant, macroscopically manifests itself by this very simple looking symmetry of the large deviation function. Whatever calculation you do, if you don't get this identity, your calculation is wrong. Okay? It's like thermodynamics. Thermodynamics tells you some a priori properties. If you compute the free energy using Bethe Ansatz and you get something and you check and it's not convex, or then your calculation is wrong. Let's do it again. So it's a bit the same thing here. And if we use this fluctuation theorem, we can, in fact, get some information about the probability of transport of some current versus the probability of transport of the reverse current. And one thing which was shown by Galavotti and which really attracted the light on this fluctuation theorem is that here you have a functional identity in red, phi of j minus very simple one. It's a functional identity which is very valid far from equilibrium. There are parameters in phi, for example, the two temperatures on the boundaries. Okay, you can specialize it to the case where the two temperatures are equal, then you get back to equilibrium. But you can take them very close to each other or very different. It's in your hand, in your pocket, to turn the knob. So now if you use this identity close to equilibrium, so the two temperatures are slightly different, then you go into the realm of linear response theory, and you can do a kind of expansion near equilibrium at first order or second order. And if you take this identity of the fluctuation theorem of Galavotti and Cohen and you expand it to first and second order, you retrieve Einstein and Onsager relations, which were found at the beginning of the previous century. So this functional identity contains at the linear and second quadratic order, you have to go to quadratic because the linear order is often trivial. At lowest significative order, you retrieve some classical results which were known before. But of course, you can expand it to the third order, fourth order, and get some new identities that people were not aware of before. Okay, I think I will finish very soon. The general problem we want to address is the problem that combines both current and profile. What is the probability of seeing a current small j, which is different from the typical current capital J in blue, and seeing a profile which is non-linear, different from the linear Fourier profile in dotted blue lines. So you can define the probability distribution on the local currents. Even current is something is local. You measure current somewhere on your wire, and on the local density rho. So this distribution of these two quantities, rho and j, it will adopt a large deviation behavior, which depends on some functional capital I on j and rho. And if you were able to say something, to compute this functional distribution, functional large deviation function I of j and rho, if you were able to compute it, then by taking some averages or taking some marginals, you would know the distribution of the current unknown or the distribution of the density unknown. And the question is, can one compute this I? How can you get it from physics principle? Is there a principle which allows you to compute this capital I? And I'm going to finish here. This is precisely what this macroscopic fluctuation theory, which will be the subject of the fourth lecture, does, which was developed by a Rome group on Gionnalazino, Bertini, Da Sole, Gabrielli, and Nandim. These people postulate, and motivated by some example, exactly solvable models, optimization principle, kind of Allaire-Lagrange action principle that allows you to compute this functional capital I, this large deviation functional of the current, joint large deviation functional of the current and the density as the minimum of some quadratic functional, quadratic in current but nonlinear in density of j and rho. So I will, of course, explain that much later. I just wanted to flash that now, for some systems, it's not totally general. The systems have to be diffusive. It doesn't work for ballistic systems yet. But for some systems, under some hypotheses, but quite large class of systems, the exclusion process is one of them. There is a kind of physical principle, which in principle would allow you to compute this large deviation functional capital I through an optimization procedure. Okay, you know what to optimize to get it. Doesn't mean it's simple, okay? Because once you have this minimization procedure, you can write some, you can write some equations, Allaire-Lagrange equations that optimize this action. And these equations, unfortunately, are hard to solve. So physicists are happy because they get some PDEs, And PDEs are something we're used to in hydrodynamics, in electromagnetism. But unfortunately, these PDEs are a bit bizarre and they are not so easy to solve. But it happens so, and this was just found a year ago, and this is going to be part of the subject of the fourth lecture. These PDEs are classically integrable. They can solve, at least for the exclusion process and some nice models, they can be solved by using inverse scattering procedure. So here, classical integrability helps us to understand these PDEs. Do I still have half a minute? Sure. So I'm going to tell you about the 20 transparents that were left. So the idea is I want to connect with the other lectures today. The idea is this model of physics is much too complicated, electrons, wire, metal, reservoirs. No, you don't want to know about that. So we prefer to look at simple models like the exclusion process, just as we like to look at the Ising model instead of a true magnetic material. But of course, if you go to a solid state physicist and you show to him or to her the Ising model, she will laugh at you. I mean, a true magnet is not the Ising model, but the Ising model contains a lot of things. So this exclusion process, we are going to hear a lot about particles making random walks, continuous time random walks on a lattice, with the fact that you cannot have two particles at the same time at the same site. So some hops are forbidden. You can connect it to reservoirs, you can wrap it on the torus, you can put it on an infinite line. All this is a beautiful bunch of works which go in many different directions. So this model will help us to answer some questions that I have presented in the previous transparencies. One has to remember that this model was invented by biologists, not by mathematicians, not by physicists, not by chemists, by biologists who wanted to understand how RNA is translated in the cell. So they really, in 1968, these three people, Caroline MacDonald, Gibbs, not the same Gibbs, and Pipkin, but they really invented the model. And then it was taken over by probabilists and then by physicists to become a pure mathematical model. And this model will really help us to understand how things go, because this model, which is a microscopic stochastic process, can be mapped exactly in some cases, and then with twist into Heisenberg type models, spin chains. And fortunately, for not all, of course, but in many, many cases, this model is quantum integrable. It has, it can be solved by Bethe Ansatz, coordinate, or algebraic Bethe Ansatz. And then many of the questions we were asking about large deviations of the current, of the profile, and so on, can be solved by using these tools. There are some more elaborate tools that can be used, which are the so-called integrable probabilities when we want to study models on infinite systems. And I just told you, in the continuous limit where you forget about the lattice and you write kind of hydrodynamic equations to describe this model, which are the ones I just showed you before, you get these macroscopic fluctuation theory equations. Then these equations, they can be solved by using, don't worry, I'm not going to tell about that today, by using the inverse scattering method. So there's a kind of tension here again between micro and micro. Micro can be solved using Bethe Ansatz and algebraic tools. Macro can be solved by using inverse scattering wave theory, nonlinear wave theory. And it's quite beautiful because they talk to each other and it's plenty of open questions. We don't really understand. I don't understand, maybe other people do, how these different levels communicate. And of course, there are many open questions that are not yet addressed. Thank you. Thank you very much.
You showed the formula for the large deviation function in terms of free energy. Of course, I mean, this you would.
This one, for example?
No, it's just f of rho minus f of rho.
Yeah, it's almost the same.
Yes.
This is the local one at one point. The other one is for the field.
I mean, you think when you look at such a formula that it's going to be the second derivative of f, but of course, I guess this is not what you.
So you're perfectly right. It's a second derivative of f when rho is close to rho zero. But this formula is valid even if you have a local density, which is twice as big as the average density, not only epsilon. But if you do this at second order, you retrieve thermodynamic fluctuation theory of Einstein. Yeah, thank you. That's a good question, of course.
Is it hard to show? I mean,
No. It's an exercise I give to my master's students. or yeah,
So you will show it.
no? Exercise. It's a StatMech exercise. It's quite, in fact, if you think about it, you'll find it in a few minutes. It's really basic StatMech.
Yes, so I had a question about this asset model, which I guess you will talk about more in the next.
And not only me, of course.
But is there a free fermion points similar to the XX limit of the XX chain, where you can get exact results which are more explicit than Bethe Ansatz solution?
Well, Bethe Ansatz is quite explicit.
I mean,
No, so that's a good question. Probably Vincent will answer much better than I do. I would say no, not exactly a free fermion point, because but there is no free fermion point for the. It's really XXZ.
Actually, that's a question which is not so obvious.
Yeah,
There is this set, then you can take three fermions. Of course, three fermions are not the same as seven.
exactly. So that's what I was going to say. So if you write ZAP and you map it, there's no approximation. The mapping is clean. There's a mapping to XXZ. And the delta is not zero.
yeah,
The delta, in fact, cannot be zero because you have a stochastic process.
it
And it
doesn't
has-
depend on the alpha, beta, etc. You cannot like fine tune it like in the
No,
6 versus
No,
model.
no, no. In fact, you cannot fine tune it, and you have to. In fact, it depends on alpha, beta, and so on. But its sign is positive. I mean, because these rates are positive. Of course, if you take alpha, beta complex or whatever, you can make it to be zero. But no, we don't want that. We want something which describes the stochastic process. So no, we cannot. But, and this is precisely what Vincent was alluding to, very strangely, when you do calculations, first of all, when you use Bethe Ansatz, you can say Bethe Ansatz is like a classical integrability. It's a way of breaking your system into independent oscillators. An independent oscillator is a free fermion, if you want. It's
Yeah, but I
independent.
mean, solving the Bethe Ansatz equation.
Solving the Bethe Ansatz
you
is a way of
always-
mapping your system into a system of free fermions. But of course, everything is embedded in a change of variable. I mean, it's not exactly true, but it's a way of diagonalizing it. But this is not I agree, it's not a good answer. It's not. But what happens is that once you do your calculations using the Bethe Ansatz and doing all the tough thing, sometimes, not for all quantities, some quantities you get are very similar to free fermions at finite temperature. And I think this is not well understood why. As far as I know, it's not really understood why you get the same. But yeah, definitely, and I remember having a kind of strong conversation, kind of, heated conversation with somebody we all know, but I'm not going to say who it is, who's not here. Definitely, ZAP is not free fermions. But somehow, Bethe Ansatz allows you to solve it, so to diagonalize it.
Can I ask about the appearance and role of integrability? So in your macroscopic fluctuation theory, you ended up with a set of integrable PDEs. Was that because you started from an integrable system, or is that the general?
So this is, of course, a very, very good question. Up to a year ago, so people have been, so these equations were proposed, okay, it took a time, and it really began roughly 20 years ago, but in this form, they were written less than 10 years ago. And people starting doing, the problem is that, for example, you have a minus sign on the second derivative, on the second equation. So of course, it's a bit ill-defined, it's stiff, heat equation with the minus, with a negative diffusion. But okay, these equations are only valid. They blow up in finite time. So people started trying to do many things, numerical simulations, which are not so easy, perturbative calculations. Equilibrium, there is one trivial solution, which is P equal to 0, and Q is given by Fourier law. And then you can do perturbation. People try to solve it by WKB method. And there were indications that somehow you could do more than what you thought. I mean, if you take equations and you try to do some calculations, naive calculations, perturbative calculation, you do it for the first order. But for example, I remember maybe 6-7 years ago with two of my colleagues, Philippe Sadou and Paul Krabowski, we could do some perturbative calculations to the fifth order. And we had some kind of integrals that we had to compute just by doing perturbative, which were 6-fold integrals, but we could reduce them to 1-fold. So this was an indication that something was escaping us and some structure is underlying it. So this was the way that people came to the idea that it may be integrable. Now, it's true that many people, including myself, were saying that because the exclusion process microscopically is integrable, maybe the hydrodynamic limit of it, which is these equations, should be also integrable. But then people would answer, rightly so, no, this is bullshit. I mean, it's not that because the microscopic model is integrable, you have an infinite number of conserved quantities. You go to a kind of coarse-grained limit, you lose everything. Why should it be still integrable? This is not, so it's kind of wishful thinking. It worked for the exclusion process, hopefully, without using this dictionary, just by chance, the equations, but there's no general rule. And even a contrario, there's one model that has been explored by MFT, which is a heat transfer model, which is called the Kipnis-Marcurow-Presutti model, KMP. And the basic version of the KMP is not microscopically integrable. It's a simple model. You have lattice sites, you have masses or energies on each site, which are continuous real numbers, positive numbers, continuous. And each time you choose a site, which is I, it has energy EI, and you break EI into you cut it in two pieces, EI1 and EI2, which are unequal, and you give it to the boundary one, to the two adjacent ones. So you redistribute mass or energy like that, and let your system evolve. You can put reservoirs and so on. So this is a very nice model. It's not integrable, but the MFT equations of it are integrable. And then more recently, I got the name, Christian Giardina, found a microscopic version of the KMP model, which is not the one I just told you, slightly more complicated, but which is microscopically integrable. So there's a kind of tension between these two, but no theorem.
But are there other examples of theories for which the macroscopic fluctuation theory is not integrable?
Yes.
Yeah, there are.
Well, there are plenty of examples of microscopic models which are not integrable. For example, exclusion process with 2. You can put at most 2.
But then the hydrodynamic description, is that also not integrable?
And the hydrodynamic description seems to be not integrable. Of course, it's not easy to say that something is not integrable. It's just that it doesn't pass the tests that you know. But there could be a more intelligent test that you don't know that could be passed, but likely not to be integrable.
Any other questions? Oh, okay, let's thank Kirone. Yeah.